Hello everyone, I am Milan Groshev, a PhD student from University Carlos III of Madrid, and today I'm going to present COTORRA, a context-aware testbed for robotic applications. This work we did with my colleagues Jorge Martin Perez, Kirill Antevsky, Antonio de la Oliva, and Carlos Jesus Bernardo from UC3M. First, what is the goal of our work? The main goal is to propose a context-aware testbed for serverless robotic application that lives at the edge of the network. The second goal is to showcase the implementation of such testbed over commodity hardware and validate the testbed by running an orchestration and federation solution on top of it. To do so, I will start with an insight on what is edge robotics as a concept and how the serverless computing fits into it. To detect the gap in the existing literature, I will give a brief overview of the robotic testbeds today. Afterwards, I will present COTORRA as a pluggable, context-aware testbed composed of hardware, core, and plugins layers. To better understand COTORRA, I will present its implementation in a scenario that we executed in the university. This scenario will be later used to experimentally validate service orchestration and DLT federation mechanisms for robotic systems. At the end, I will conclude the good work with the main outcomes. Let's begin with what is edge robotics. Edge robotics is considered as a potential extension of cloud robotics where edge computing resources are integrated in robotic systems to allow real-time applications to run closer to the robots. Moreover, real-time contextual information is available in the edge that allows dynamic adaptation of applications logic to the actual status of the communication channel or other aspects of the environment. For example, on the figure, we have an edge robotic service where the robot brain presents the virtualized robot control that communicates with the robot in order to execute navigation commands. On the other hand, the robot sends back the sensor data. Although edge computing appears as the straightforward extension for offloading time-sensitive robotic application, such scenario cannot be simply supported by the traditional virtualization and containerization technologies. The distributed and resource-constrained nature of the edge infrastructure imposes limitations regarding its capability of hosting diverse robotic applications and services, since an overloaded edge server significantly degrades the robotic performance. Serverless computing arises as a possible solution where different robotic functionalities can be executed and runtime invoked by different types of events. In our example, upon receiving of a navigation request, the serverless platform will decide the resource allocation for the execution of the robot brain in order to navigate the robot. Once the robot arrives to its destination, the allocated resources will be released. The evolution of robotic applications depends on the testbeds where you can run and test the innovative applications under different scenarios. Most of the existing testbeds for robotics focus on cloud robotics. On this slide, we have some examples of testbeds like VCBots, Araputua, OpenCloro, all of them that address different implementation, development, and network-related issues for cloud robotics. Unfortunately, no context-aware real-time robotic testbed is explicitly mentioned in the existing literature, despite the need for an analysis on implementation issues, standards, and validation of edge robotic applications. There is a lack on practical experience on context-aware real-time environments in robotic systems. That leads to limited applicability in production systems and final products. Motivated by this, in this work, we present COTORRA, a context-aware testbed architecture that operates at the edge of the network. The COTORRA architecture presented on this slide is designed to work with serverless plugins that interact with the hardware infrastructure and retrieve its context information using the COTORRA core layer. In the following couple of slides, I will present each of these layers in more details. I will start with the COTORRA hardware layer that is composed of robots, network, and computing infrastructure. The robots consist of sensors like LiDAR or camera that produce stream of data and actuators that actually move the robot joints or wheels. Next, The network infrastructure is responsible for connecting the robots to a computing infrastructure and is composed of network elements like wireless access points, routers, or switches. Finally, the computing infrastructure embodies any computing device ranging from end devices like mini PCs and laptops to powerful servers. Next is the COTORRA core layer that is represented as a set of building blocks, namely the robot middleware, network control, and measurement building blocks. Every building block has an API to interact with the hardware layer and report data to the plugins layer. The robot middleware building block periodically collects, stores, and exposes a real-time robot sensor data and sends instructions to the robot. The contextual embedding is stored using the measurements building block and exposed to the plugins in real time. The measurements building block stores and exposes a history of every embedding. The available historical data ranges from robot sensor data to network contextual information and is exposed via the measurements API to the plugins layer. The network control building block interacts with the domain infrastructure to collect, expose, and store network and radio unit contextual information. One of its main functionalities is also to emulate network conditions in order to provide unpredictable environment where new pluggable applications can be tested. Finally, the network control acts as a virtual infrastructure manager that helps to deploy the virtual functions in the underlying domain infrastructure and maps, stores, and executes virtual functions and virtual links in the hardware graph. On top, we have the COTORRA's plugin layer. COTORRA offers the testing capabilities through the plugins layer. A robotic application in COTORRA is composed of one or more serverless plugins. Each serverless plugin is a robotic functionality, like for example, orchestration, navigation, or maybe motion planning functionality. Serverless plugins are executed either as containers or virtual machines that implement the APIs to interact with the COTORRA core layer. They consume periodic contextual information from the testbed in order to develop their logic and define various types of invoking events. Additionally, the plugins can also interact with the testbed by sending instructions to the robot via the robot middleware or perform deployments of virtual functions via the virtual infrastructure manager of the network control. To showcase the design testbed, we implemented COTORRA in the university hallway. The figure shows an implementation of COTORRA testbed on a mobile robot. The COTORRA hardware layer consists of 5 ASUS access points running OpenVRT that were distributed along the university hallway to ensure full coverage, 5 mini PCs, from whom 2 mini PCs are used as virtual access points and the rest as servers. 2 of the server mini PCs simulate far edge and cloud, and 1 is representing the near edge. 1 switch interconnects all the nodes, and a Kabuki Turtlebot mobile robot was used that was equipped with a LiDAR. The COTORRA core building blocks are implemented using containers. The robot middleware building block is deployed in the server nodes and is implemented using ROS. It collects and exposes the LiDAR and odometry sensor data from the mobile robot to the plugin layers and sends to the robot the navigation instructions. In addition, as part of the robot middleware building block, we deployed a localization service to provide probabilistic robot localization. The network control is distributed among the servers and the access points. Each access point contains a robot network information service to provide real-time context information regarding the communication channel. In addition, the network control emulation capabilities are implemented using emulation tool called NetEm to introduce artificial latency and packet loss. For the network control virtual infrastructure manager functionalities, we've used FOGO5, and for the measurements building block, we used MySQL database. Finally, our COTORRA implementation used a ROS Brain as a plugin to provide autonomous navigation for the mobile robot along the university hallway, following the trajectory that is shown on the figure. To validate our testbed implementation, we run on top 2 different serverless plugins that can enhance the autonomous driving service. The first deployed serverless plugin in COTORRA was OKPI, a service orchestration algorithm that decides the deployment of virtual functions and virtual links to meet latency constraints. Additionally, OKPI also considers coverage constraints and tells a robot to which radio unit it has to attach to experience low latency. In the experimental validation, OKPI was deployed in the cloud server and it had implemented the COTORRA core layer APIs. During the experiment setup, the network emulation capabilities of the network control building block were used to inject delays in the link connecting the access points with the edge and cloud servers. The table at the bottom of this slide shows the details regarding the delays injected and the access points deployed in the testbed. The goal of the delay injection is to introduce latency heterogeneity. Once the experiment starts and the robot moves along the hallway, OKPI periodically consumes real-time data about the link delays, current robot position, and current access point attachment, and in each point of time during the drive, OKPI specifies the best access point candidate that does not validate the latency constraints and instruct the robot to perform handover to that access point. Moreover, it selects the best location for the autonomous navigation plugin between the near edge, far edge, and the cloud, and contacts fOR to perform the deployment. The results show a comparison of what is the service time experience when the autonomous navigation is enhanced with the OKPI plugin and when it uses a state-of-the-art solution consisting of cloud robotics scenario doing handovers based on single-strand periodic Wi-Fi scans. The obtained results show that OKPI plugin enhances the autonomous navigation by maintaining a service time below 15 milliseconds. Moreover, it reduces the number of Wi-Fi scans with respect to the state-of-the-art due to the OKPI triggered handovers, in which case the robot does not have to periodically scan the Wi-Fi channel. The second deployed robotic mechanism in COTORRA was a DLT-based multi-domain federation concept. Service federation is a procedure that enables orchestration of services across multiple administrative domains. The experiment consists of moving robot towards out of a coverage area of domain 1, as shown in the figure, and extending the connectivity range on the fly in domain 2. A serverless orchestrator plugin is deployed in each of the domains, and a DLT plugin is used for inter-domain interaction. The mobile robot moves from a starting position towards the coverage area of domain 2. The robot brain analyzes the localization data from the network control and triggers a federation event to the domain 1 orchestrator that starts the federation of virtual access point procedure through the DLT plugin. Both orchestration negotiate through the DLT plugin and the deploy virtual access point event is sent to the domain 2. The domain 2 orchestrator initiates the deployment of a virtual access point and the mobile robot attaches to the newly deployed virtual access point in domain 2 without any interruption of the service. The results show that both orchestrators negotiate for 4 seconds and the domain 2 orchestrator deploys the new virtual access point for less than 6 seconds. Domain 1 orchestrator awaits confirmation for 8 seconds and instructs the mobile robot to switch to the new virtual access point. The whole federation procedure takes around 19 seconds to complete. This brings us to the conclusion of this work, where we introduced COTORRA as a modular and serverless context-aware testbed for robotic systems. We show how COTORRA can be implemented over commodity hardware, offering support for rapid prototyping. We validated COTORRA by running OKPI to achieve autonomous navigation service latencies below 15 milliseconds, and we ran inter-domain DLT federation within 19 seconds. Thank you for your attention, and for the end, I would like to mention that this work is partially funded by 2 H2020 projects, 5G Growth and 5G Dive.